what I label, obviously. All right, so we have two different types of reactions here. Okay, remember, these potential energy diagrams, the energy is on the y, so label that PE, potential energy. And then on the x, we can put reaction coordinate. I'll just put reaction progress, RXN progress. So in other words, from start to finish, that's what that means, reaction progress. All right. And if you don't mind, take one more thing out. Table I, please. Reference table I. I know, a lot of stuff. A lot of stuff going on. So I'm going to give you a little bit of notes here, then we'll go back to the homework, and then we should be able to end with the demo. All right, so we'll go to table I in a second. So I'm going to label what I think are the three most important parts of this thing here that the Regents ask the most questions about. So I'm going to label the activation energy. Okay, so I want you to do that. So we'll label that number 1. And then what we're going to do is we're going to put a little X on the top, and we'll label that number 2. And then what we're going to do is draw a dotted line from the reactants here, and then the product. So do something that looks like that. And let's label that. Let's label this a P, standing for products. And then let's put an R right in the beginning here for reactants. So our reactants are right here. Our products are right here. Arrow 1, X2. And then we're going to have another arrow right here in between R and P, and label that number 3. I'm not going to do all of them over here because they're the same. Number 1 and number 2 never change. They're always from, number 1 is always from reactants to the top of the peak. So we can label R and P here, that's fine. So reactants to the peak, that's always your activation energy. So I'm not going to label it twice. X on top, that's your activated complex. That's always the same. I'm not going to label it just to make it a little cleaner. But I am going to label number 3 the same here. So I want you to do that. We actually don't need to make a dotted line there. So there's we'll do number 3 again there, just to keep it consistent. And then underneath them, maybe write some notes. I'm just going to put it over here on the side. So number 1 is our activation energy. Activation energy, and again, that's of the forward reaction. That's supposed to be a parenthesis. That's pretty bad. Forward reaction. What does forward mean? It means going from reactants to products. That's like the normal way reactions occur. You can reverse reactions, but that's called reverse. So the forward is from reactants to products, so going left to right. So what is activation energy? It's the energy needed to start a reaction. Energy needed to start a reaction. That is the activation energy. Yesterday I showed you the demo. The hot glycerin, I poured it on the potassium permanganate, the one on the right. The hot one reacted very quickly because what we did, look up here, we took the reactants and we gave them energy and bumped them up to the top. Once the reactants get to the top, they can start to collide and react. So giving it energy, right, heating it up, you're giving it a boost. It gets up to the top faster. That's what the point of that demo was. So I gave it more energy, reaching that activation, reaching that activation energy quicker. Number 2, activated complex. Activated complex, and that's sometimes called the transition state. Sometimes called the transition state. And what happens here are the effective collisions between reacting particles. Effective collisions between reacting particles. So your reactants, that's where they collide. And hopefully they collide effectively, right? Enough energy, proper orientation, then they will continue down the other side of the hill and form products. So right at the top is where they do their colliding. But they can't get to the top unless they have enough kinetic energy, right? So that's the activation. So you need both. You got to get to the top first, and then hopefully you have the right orientation to actually make products. So that's number one. That's number two. I'm going to erase this so I have more room to talk about number three. Questions so far? Very common Regis questions asking about these two. Okay? What is that? What happens? What is that? What happens? Okay, it could be multiple choice, short answer, usually multiple choice. But we're good. Okay, number three. What's number three called? Michaela? In between your products and your reactants. What's that called? I know it's confusing. There's a lot of lines on there. So you're looking, so here, look up here. You got your reactants and you got your product. And I think, oh, yours looks like this. So you got reactants and products. What's in between those two? Delta H, very good. So 3 is the heat of reaction, which is called, or the symbol is delta H. What does delta mean, Marcy? Change. Good. Change or difference, right? Change or difference. So change is good. So it's the change in the heat. So I'm going to label these. So let's say this is 0 here. Let's say this is 100 here. Let's say it's kilojoules. Put that in parentheses, right? Their unit, 0 and 100. So let's say the reactants are, I don't know, let's just say 30, right? Let's say the products are 60. Okay, over here, let's do the same thing, 0 and 100. And we have kilojoules here, reactants, products. So let's say products, well, we'll keep it consistent. Products are 30, reactants are 60. Let's just keep it consistent, even though it doesn't look perfect, but that's fine. It's close. All right, we'll come back to that. So what is delta H? It's the change in the amount of heat or energy. So I'm going to write heat / energy. The change in the amount of heat or energy, I want to make sure I word this as clear as I can. The change in the amount of heat or energy between products and reactants. The change in the amount of heat or energy between products and reactants. I don't even like that very much. So, write it, that's fine. But basically, another way to say that is how does the reaction progress in terms of energy? Is it releasing energy or is it absorbing, right? So this tells us if a reaction is endo or exo. Endo or exo. Exothermic, endothermic, I'm abbreviating. That's what the delta H tells us. And here's how we get it. One more little star here, and then we'll calculate these things here. We always do the products minus reactants. That's how we use, or how we find delta H. The product heat minus the reactants heat. I technically forgot the word heat. So products heat, reactants heat. When I say heat, I mean energy. Same thing. It's always products minus reactants. Always. That's how we know if it's endo or exo. So, if we look at this one here and this one here, we're going to get opposite signs. Right? Opposite signs. So if we take the product energy minus reactant energy, Kaylin, what numbers am I subtracting? What minus what? 60 minus 30. Underneath here, hopefully you have room here. If not, put it somewhere near this. Delta H equals 60 minus 30. So 60 minus 30, what's that equal, Laura? In the back? Positive or negative? Yeah. I wasn't trying to trick you. Plus 30 kJ. Plus 30 kilojoules. Put the plus sign. Positive 30 kilojoules. That's for this one over here on the left. The one on the right, delta H equals. Now, Pat, what are the numbers we're subtracting?
30 minus 60.
30 minus 60, very good. 30 minus 60 equals, Kira? Negative 30 kilojoules. That's a different ball game. All right, Max, ready? Which reaction, so this one positive 30, this one negative 30, which reaction is endothermic, which one is exothermic? And hold on, someone's going to help refresh your memory. Laura, what does endothermic mean? Takes or absorbs energy. Good. So what's exothermic? Gives off or releases energy or heat. Good. Okay, Max, so which one is endothermic? Which one is exothermic? Very good. This is exothermic. Good job. Exothermic. This is endothermic. Very good. There's two ways you can figure this out. Mariana, want to know both ways? Yeah. Good answer. Okay. You can do the math. Positive delta H means endothermic. You learned that a long time ago. Go to table I. Look at the very bottom of it. Look at the very bottom of table I. It says minus sign indicates exothermic. So minus sign here, right? Look up here. Negative delta H means exothermic. Positive means endo. That's one way to figure it out. Do the math. Products minus reactants. That's one way to do it. The other way is maybe easier for some of you. Maybe more fun, we'll call it. Just look at the picture. If the reactants are lower on the energy scale than the products, that means this reaction gained energy. As it reacted, it gained energy because the products are higher on the y-axis than the reactants. So it just looks higher because it is higher, and that means it gained energy. So that's another way to say, oh, this gained energy, that's endo. Look at this one. It fell. It's lower. So as this reacted, it lost energy. Well, what does that mean? Exothermic. So the reactants lost energy at some way, somehow. As they reacted, they lost energy when they formed products. So those are the two ways you can figure it out. Do the math. Look at your chart. Why do you have table I open? If you look at that very first reaction, what's the value of delta H? What's the value of delta H? Cassie. Very first reaction on table I. Minus 890.4. So Monique, which graph could that be used to explain? Which graph, left or right, would the first reaction could be used? What? Yeah, because it lost energy. Now the numbers are wrong. They would have to be negative 890.4, but what I'm trying to show you is the regents can say, okay, given the following reaction from table I, so they give you a reaction, which potential energy diagram would work for this reaction? So they'll give you 4 choices, right? Multiple choice probably, and one of them would be exothermic. That's the one you would pick because the reaction, the first one, for example, is exothermic. But if you go down table I don't know which one it is, that first positive delta H, I think it's something with nitrogen. Yeah, N2 plus O2 yields 2NO gas, positive 182.6, that would be here. Okay, that would be endothermic, right? So, you're learning a lot right now, okay? Hopefully you're staying with me. Definitions, how to label this thing, now how to use it. How to use it to answer questions like endo, exo, how to find delta H, how it relates to table I. Okay, so all of this is important, and I'm kind of teaching everything at once. There's not much more to learn after this. All right? So questions on anything I just said? Well, we're going to go back to the homework now. I'm going to go through the homework due tomorrow. No, I got to teach you about catalysts. We still got some time. So the catalyst is pretty quick and easy to show here, and then we'll go do that demo. So I'm going to answer. Keep your notes out though. I'm going to answer the questions to the homework. I'm just going to answer it real quick because I think I just did answer all the questions, and then we will learn about catalysts really quick and then do the demo. Here we go. Number 1, in the forward reaction, who has more energy, products or reactants? So I was going to set this thing up, but that's all right. Just to save time, I'll hold it up. So reactants are up here, products are down here. Reactants have more energy. So for number 1A, reactants have more energy. And by what amount? the difference between the products and reactants would be 77.2 kilojoules. So there's a difference of 77.2. The reactants have 77.2 more kilojoules. 1b, what type of reaction? That is exo or endo. Based on what we just learned, this is exothermic. Delta H is negative, the products have less energy, that's exothermic. C, what is the value of delta H? That's really what it's asking. What is the value of delta H? And it is negative 77.2. So the answer to C is negative 77.2. Letter D, what is the enthalpy of reaction for the reverse? Is it endo or exo? Okay, so look up here. So if we're standing on the products and we want to go up and back to the reactants, that's going in reverse. So what is the delta H for the reverse? It's still 77.2, right? Let's look at this. It's still 77.2. Delta H doesn't change. But if we're going this way, what's different? It's positive. It would be positive 30 here because we're going up, right? But the difference is still the same. It's just positive going this way. So on the homework, it was positive 77.2. To go that way, it's positive. So letter D would be positive 77.2. And that would be endothermic for 1D. Because we're going this way, the reverse of an exo is an endo. Okay, so that's endo going that way. 1E, what is the activation energy for the forward? So that's from here to here. Look up here. From here to here, and that's 89.5. That's the activation energy of the forward. The reverse, look up here, we would have to add the delta H plus the activation, right? So we're going to have to go from here and then all the way up to the top of the peak. If we're starting here, that's the reverse activation energy. So that would be 77.2 plus 89.5. So that would be from the bottom all the way to the top. So anyone have that number? 166.7. Very good. Which reaction would you expect to occur more rapidly and why? Okay, so let's look at this for example right here. If we have someone standing here and we have someone standing here, let's say they both run up this hill at the exact same speed. Who's going to get to the top first? Person number 1 or person number 2? Person number 1. So the forward reaction is faster than the reverse reaction because as soon as they get to the top here, the reaction starts. So this person is going to get to the top first. This person is going to get there second. So the forward is going to react faster than the reverse because it takes more energy to get up here from here than from here to here. Does that make some sense? I hope. Good. All right. And 4, 5, and 6, I'm going to put on hold right now. So I want to make sure I explain catalysts here real quick so you can do your homework. So you can put that worksheet away. I'm going to erase this and sketch another one. And then we'll go do the demo. The demo only takes a couple minutes. Hopefully I have time. All right. So underneath all of this in your notes, let's write catalysts. What is a catalyst? What does a catalyst do? A catalyst speeds up a reaction. What does that mean? It increases the reaction rate. The rate means the speed. It increases the reaction rate. Speeds up a reaction. How does it do it? This is the most important part. It lowers activation energy. It lowers activation energy. So I'm going to sketch another one of these things over here. You do the same. And then what I want you to do is put a little dotted line like I do. So a dotted line underneath the original curve. Make sure that dotted line starts on the reactants and ends on the products. I don't want that dotted line crossing the line or going underneath it. It has to start exactly at the reactants, exactly at the products. It has to end exactly at the products. So, again, we used Pat as an analogy yesterday with a sombrero on. We can give him another sombrero here. There you go, Pat. So if Pat is going to take the long way up to the top or take the short path up to the top, which one will he get to the top of first? the lower path, right? The smaller hill, the smaller mountain bump, whatever you want to call it. So if he takes the second alternate path, he will react faster because he gets to the top where the collisions occur faster. That's what a catalyst does. It lowers that activation energy. That first arrow, okay, from here to here, it lowers that. So it requires less energy to start. Therefore, it reacts faster. That's how catalysts work. Speeds up a reaction, lowers activation energy, provides alternate reaction pathway. That's what a catalyst does. Let's go back and do the demo. I know I went quick, but that's okay.